Thank you very much, Julien, Paul, for organizing this meeting, inviting me. It has already been a lot of exchanges and so on, so I like it very much. And I think people have very different backgrounds, so I'll try to give the insights, because it's going to be a mostly computational talk, but with some links with behavior, animal behavior observed in experiments, some neurophysiology about dopamine activity in the brain, and there will be some links with Roshan Kool's presentation yesterday. And I'll show you also one example of robotic tests. So we put on the robot some computational model of dopamine function, how we understand it in the rodent brain these days, to extract some predictions. So I also show you a bit of robot behavior. It's just going to be a couple of slides so as to illustrate those exchanges between disciplines, and I think it's something also important in HBP with the neurorobotics community and so on. So the talk is about exploiting individual differences to inform computational models of dopamine in reinforcement learning. And so the main message is I'll focus mostly on a Pavlovian conditioning task in rats. And there was a paper that has received a lot of attention by Shelley Flagel and colleagues that showed that actually different groups of rats had different behaviors, what they called sign trackers, attracted by signs predictors of reward, and goal trackers, mostly attracted by reward location itself. And they had different dopamine activity patterns measured in FSCV, in the nucleus accumbens, which was puzzling to the community. So how can we explain this? And so the main ingredients that I will show you we use in the computational models to account for this is first that dopamine is important for reward-based reinforcement learning. So you already heard about this before in the previous presentations, but I'll go deeper into this. Then a second important ingredient that we use is that we don't make the hypothesis that there is a single learning system in the brain or a single decision-making system. There are actually parallel learning systems, and there is accumulating evidence in the literature about this. And we make the hypothesis that actually the behavior of these animals rely on an equilibrium between a dopamine-dependent learning process in one system and a dopamine-independent learning process in another system. And the last ingredient we used, and I will try to emphasize and convince you of the validity of this hypothesis, is that dopamine is not only important for learning, but also for behavioral expression, so translation of learned values into decisions. And more technically, but I will explain later, the idea that we formalize this very simplistically, parsimoniously, as playing with one parameter, an inverse temperature, in a softmax decision-making function, which usually is something that tunes the exploration-exploitation trade-off. And I will show you some model simulations, so how we account for this previous behavior, brain activity. But I also, after, show you a couple of experiments we did afterwards, which actually partially validate model predictions. It's always the case, like you have some that are validated, that's good, but of course the data go further, and that's a new road to improve the models. Okay, so I'm restarting from one slide you showed already before. I think Roshan Kool's presented, but she didn't spend a lot of time. So we start from this central hypothesis in the community that dopaminergic neurons' phasic activity could represent a reward prediction error signal, which is important for learning. So that is, they respond to unexpected rewards, or they respond negatively with a decrease in activity when there is something worse than expected. So these are experiments in monkeys done by Wolfram Schutz and colleagues in the 90s. And the monkeys are passive, just waiting, and there's a stimulus appearing on the screen, and here we will be represented by this vertical bar, the stimulus. And let's say 2 seconds later, there is a reward. So they receive some juice reward here. And animals, through trial and errors, will have to learn this association. So it's a Pavlovian conditioning task. What is interesting, these are the raster recording one exemplar dopaminergic neuron, and this raster has been shown so many times in so many presentations. Of course, it has been replicated by other teams. So you see this neuron initially, during initial learning, responds to the reward, because that's new for the animal. So it's a positive surprise. It's better than expected. And after hundreds of trials of training, the same neuron now does not respond to the reward anymore because it's expected, but responds to the stimulus, because that's the surprise. There's nothing in the task that enables the animal to predict the timing of the stimulus. So each time the stimulus is presented, that's surprising. And so that's a positive surprise. And you see at the time of the reward, no response. And the hypothesis is that it's as expected. There is no reward prediction error. And lastly, and even more convincingly, after training, the animals are presented with a stimulus, so they expect some reward, but it's an omission trial. They don't get anything. So of course the animals get frustrated, but in addition you see this decrease in activity as indicating that it's worse than expected. It's a negative reward prediction error. So this is a very central result in the field. And as Roshan already told you briefly yesterday, it has been related to reinforcement learning algorithms from machine learning. So these are algorithms that have been designed to enable autonomous agents to learn by trial and error. And the idea is to have a reinforcement signal delta. I reassure you, I'm not going to show you many equations, so there's going only to be a couple, but the idea is to understand the mechanism behind. So the reinforcement signal delta is computed as a sum of 3 terms. So the reward you get from the environment, plus what you expect in the future, so your value you associate to the current situation. So if you do an action that leads to a situation where there's not yet a reward, but you expect something, like you open a box and you see a lot of food, so you predict that you're going to get reward, this is rewarding in itself. This is reinforcing in itself. And minus what you expected in the past. So if you get something that you fully predicted, that means there's no need for learning anymore. So that's this key equation, and roughly, schematically, the way to explain those data is the first time you get a reward which was unexpected, these terms were 0, so you predict a positive reinforcement signal. After learning, at the time of the reward, you get a reward, but you predicted it, so the difference between what you get and what you predicted is approximately 0. So the model predicts no reinforcement signal delta. And in the case of omission, you predicted something, so this is positive, so you have a minus something positive, but you don't get anything, so delta is negative. So that's how, schematically, these models have been related to dopaminergic activity. Now, let's jump to those puzzling data I've mentioned and that we will model here. So these are more recent experiments by Shelley Flagel, Terry Robinson, and colleagues in a Skinner box where animals are waiting for, so they have a stimulus presentation for 8 seconds. And in that case, that's a lever presentation. I think the experiment has been also done with visual stimuli or auditory stimuli. And after 8 seconds, the lever is going to be retracted, and some food will be delivered in a magazine in the center. Importantly, the animals don't need to do anything. Waiting for 8 seconds is sufficient to get the reward. So it is, in principle, a Pavlovian conditioning task. Now, what is interesting is the animals are not passive. And what you see globally is a group of animals called sign trackers that get more and more attracted by the signs that predict reward, so the lever, and they actually go and engage with the lever. They bite it, they interact. So could be that part of what they learn is some superstitious behavior, thinking that interacting with the lever produces something. But that's yet an open question in the field. And you see goal trackers are more attracted by the goal location, the reward location. But they are not passive either. There are some other papers showing that they actually also engage with the goal. So what is clear for the specialist, and I'm not, of Pavlovian conditioning is that it's really a Pavlovian process that any sign that predicts, that enables the anticipation of reward triggers some really basic behaviors of approach and engagement with this thing. So this is the behavior that they have observed. So these are the probability of approach to the lever, and on the right is to the magazine. And you see that sign trackers progressively, sessions after sessions, increase their probability to approach the lever, while the other animals do it. The goal trackers don't do it, and you have an intermediate group that is difficult to categorize in between. The goal tracker progressively increase their probability to approach the magazine. And so you see these differences in behavior. Now, what is super interesting compared to the dopamine classical reward prediction error hypothesis is that you do see this profile only in sign trackers, but not in goal trackers. So what is shown here is FSCV signal in the nucleus accumbens, sessions after sessions. So now the sessions are organized vertically, and you see again the first vertical line is the conditioned stimulus, the appearance of the lever. The second vertical line is the unconditioned stimulus, the reward delivery in the magazine. And you see initially a peak in response to the two events, but progressively the peak in response to the expected rewards vanishes, as if it's now well predicted, so there is no dopamine activity here. So that's classical. That's what people would have expected. there is a reward prediction error signal in dopamine activity in these animals. But now look at goal trackers. You see that the peak at the time of the reward is preserved, doesn't disappear, as if there was not the same profile, as if something else is happening. And that was puzzling. How can we explain this? So is it that the classical reinforcement learning algorithm well explains the behavior of only subgroups of people, or animals in this case, and not others? So our explanation is that actually it is still there, but because there's an interaction between different learning systems, and maybe there are different weightings between the contribution of these different systems between animals, that's what would be the explanation. Now, a third and very interesting result is the authors have blocked dopamine receptors systemically with flupentixol that is injected, so it has an effect throughout the brain. And what they did were 7 sessions of training in this task under flupentixol compared to saline injection, so control condition. And you see that sign trackers, the progressive increase in probability of approach to the lever now is no longer present. So it relies on dopamine function. And you see that at the 8th session, there is no longer flupentixol injected, and you see that the behavior is still impaired. So the probability to engage with a lever in the sign trackers now is significantly lower than controls. Now the same manipulation in goal trackers, during the 7th first session, it looks like they are acquiring slower the probability to go to the magazine, but at the 8th session, when you stop injecting flupentixol, the behavior is no different. And that's very interesting, because it looks like there has been a covert learning process. Maybe dopamine blockade has blocked the expression of this behavior, but not necessarily the learning, so that when you stop blocking, behavior is as if the animals had well learned. Okay, and that's a key ingredient for us to say that maybe it's another system whose learning process is dopamine independent, but maybe it's the expression that is affected by dopamine blockade. And so I will again remind the 3 main ingredients that I will show you evidence for and that we will integrate in a computational model to account for this. So dopamine reward prediction error signals may be required for something that we call model-free reinforcement learning that I will explain, but not model-based reinforcement learning. Dopamine function may not be restricted to learning, but may also modulate behavioral expression. But last but not least, and I will try to convince you, and that was something that was key for us to really succeed in explaining those data, we think that there's also some properties of the task, environmental characteristic, that play a role. And here the duration of the inter-trial interval, how long the animals are going to wait before the next trial, seems to be key. And I will show you that in the model, that's also one way we account for the data, and I will show you later experiments where we manipulated this parameter. So what do I mean by this distinction between 2 learning processes from a computational point of view, which we call model-based versus model-free reinforcement learning? So the idea is that an agent facing an environment and having to learn regularities of the environment, how to act to get reward. The agent could either try to learn an internal model of the environment, and in a navigation task like the Morris Water Maze could be a cognitive map, something I guess you're familiar with, where you learn what are the different states of the task and what are the possible actions that make you make transitions between these states. So through latent learning, you can progressively learn. So when I'm here and I'm going to the west, I think, well, I'm not completely sure, I will arrive in this new state. And I can, if I do this several times, I will see, okay, 99% of the time, this action in this state led me to this other state. So I can learn and build a mental graph progressively. So it could be a cognitive map of this room, could be a cognitive map of Nijmegen or part of Nijmegen if I need to navigate within it. And that's one strategy. The interesting thing is so here in Morris Water Maze, you have a goal location, and there is a reward here, so it's a hidden platform. But if you change the goal location, one trial is sufficient with this strategy to update your map. So there is no longer a reward here, but there is here. And then you take some time propagating information in your map to find the shortest path in a graph. So from a computational point of view, we know that's a strategy that is very flexible to changes in the environment. But it's very costly computationally, because finding this shortest path, if you have a big map to manipulate, can take a lot of time. So it predicts also longer reaction times. an alternative strategy, and it's interesting because in machine learning, these are two learning strategies, and you have classes of algorithm from one family or from the other one. And in different situations, we find that it's more appropriate to use one or the other. An alternative strategy could be for the agent to be model-free, not try to learn a model or a map of the environment, but rather learn locally in each state what is the best action to perform. So by trial and error, I've learned that I should go there. And I'm not thinking when I decide what will be the consequence. It's just that that's the action with the highest value. And what is interesting with this is computationally it's much cheaper, because you just learn to store values associated to all those actions. And after learning a navigation task, well, let's say the reward is here, what you have learned is a vector field. So it predicts the agent would be attracted toward this part of the environment. Now, the drawback of this strategy is that it's very inflexible. So if you change the task, so now the goal location is there, you will need by trial and error to update all those associations. So first, experience with reward, you will reinforce this action, but you will remain attracted by the previous goal location. So there are different properties of these two learning systems, and in machine learning it's common, and we study more and more also in robotics how we can take advantage of one or the other. Now, this framework has already been applied to neuroscience and to different behavioral paradigm in the last years. So it has been involved in instrumental learning, and that's work from Peter Dayan and others that you refer to, Paul. But it has been applied to navigation, and we also contributed to this. And more in Pavlovian conditioning paradigm, it seems that it's also relevant. There are also cases of more flexible adaptation to changes of the task versus less flexible. So the message here is that we propose to apply also this dichotomy and think it's relevant to account for goal tracking versus sign tracking behavior in what I've shown you. I thought it could be useful also because it's partly a summer school, and I guess a lot of you are not so familiar with how to apply those models. I wanted to show you an illustration of how it works in navigation, more concretely. And actually with one example of where we put the model on a robot. So this previous work that was done by Laurent Dolé during his PhD thesis. So that's the kind of models that we have. It's more like systems level models where we have different learning strategy. We have a cognitive mapping model-based strategy with hippocampal place cells. The agent will learn this cognitive map with the information from place cells and will propose decisions by planning in the graph. We have another system which is more like model-free strategy, which associates cues that are perceived in the world to action. So this more stimulus response, or what I showed you, this model-free behavior. We have another system that is random, and that's very useful to help the agent get out of dead ends and so on. And we have a hierarchical organization, so we even have what we call often a meta-controller, which will learn to select not actions, not, for example, going north, south, east, west, but will select which strategy is the most efficient at a given moment. So this is exploration, direction, or model-free, and the planning system, model-based. And from different inputs, it will learn that in different situations, different strategies are efficient, and learn it autonomously. And so it's a sort of artificial micro brain that we will put in our robot, but it's also to illustrate how we have to think in terms of system of interaction between systems to really produce behaviors that look like what we see in animals experimentally. And so with this work, we have addressed, these are illustration of 6 different navigation paradigms with Maurice Water-Maze, variations of the task, rapidly changing goal location every 4 trials and all these things. I will not go into the details, but it's really because we have this multi-system level and this interaction that we manage to account for this variety of tasks and the behavior of rats in this task. But what we also did in another European project where we built an artificial rat robot, and we worked on different aspects, but I was focusing more on the navigation part. We control the robot with the model I showed you. And in that case, what is interesting, so we do a sort of arena navigation that could be like the Maurice Water-Maze task. You have external cues, and the robot has to go to these blue points here, which is invisible to it. And on this photo, you see overprinted the cognitive map of the robot with different dots representing different artificial place cells. But what is interesting, when you have a robot do a task like this, it's very noisy. There are many things that are unexpected. And the map that is learned by the robot that you see at the top right is good, but not perfect. And so there will be cases where even using your cognitive map will not lead to the best strategy. So if at the bottom left, the goal that you have to reach ends up away from the nodes of your map, it will be difficult to plan a route to that place. While if the goal, by chance, is close to one of the nodes, it will be very easy for the robot to reach it. And so as a consequence, when we have a pure model-based only strategy controlling the robot, it will learn part of the task. It will learn to plan to go there, but then it will be random until finding the goal location. While if you combine the two, with the model I showed you, as an emergent property, we didn't tell the model, it learned autonomously to first start being model-based, plan, and then use the model tree to fine-tune the behavior based on the cue information. And that's something interesting, because we think it's interesting both for roboticists to say, well, we couldn't take inspiration from how in the mammalian brain we think different learning strategies are coordinated, and maybe there are some cases where it's more efficient than trying to find the optimal strategy. But it's also interesting for neuroscience and behavioral experiments to say, within a given trial, sometimes an animal may have a behavior which is a result of a hybrid strategy, a sort of cooperation or alternation between two different strategies. So that illustrates you how this type of models and multi-learning system models work. Okay, so I hope this was clear, and I will now jump. So that's the first ingredient important to account for the data, multi-system learning. And in our words, even if it's a caricatural dichotomy and it's more complex than this in the brain, the idea of a combination of model-based and model-free learning. Now, the second ingredient I told you is that dopamine, and in particular tonic levels of dopamine, tonic innervation to part of the brain, may also modulate behavioral expression. And we actually proposed the hypothesis that tonic dopamine could modulate the exploration-exploitation trade-off via the basal ganglia, which would be one way of controlling this behavioral expression. So in the literature before, several people have related dopamine to exploration and found actually some effect, but it's not clear exactly what were the mechanisms and in which part of the brain it would mediate this. So with Mark Humphries and Kevin Gurney, starting from a previous model of the basal ganglia and a quite neurophysiologically plausible model with different nuclei, so the striatum, subthalamic nucleus, globus pallidus, substantia nigra reticula, and the connections between those nuclei is really respecting what was known in terms of physiology, time of conduction of signals between the different nuclei and so on. And we played with this model, and we had the intuition that playing with the tonic dopamine level there, which modulates the gain of input from the cortex, would actually affect the exploration-exploitation trade-off. So we did simulations with different input profiles. So this could be 10 possible actions. So it's very abstract simulations, but it's just to show you how we did this process. So it could represent 10 possible actions with different probabilities a priori, and one that would be preferred. And then this goes through the basal ganglia, and we look at the level of the output, and we translate this output into a probability distribution. And you already see the central mechanism, which is like, if you have no dopamine, the output would be flat. So you have no preference for something, so you have difficulties to select even an action. Could relate actually to some Parkinsonian patient's deficit to initiate an action. But if you put a lot of dopamine, then this distribution will be very peaked. So you have a strong preference for one action. And if you put less dopamine, something intermediate, you see that you will have a less peak distribution. So this can be translated into the modulation through an inverse temperature parameter beta of the translation of values into action with a softmax function. So this is something that's classically used as a decision-making function. You have an input distribution that represents your action values, and if you have a low beta, then this distribution will not be too much peaked, so you have a high probability to explore. You still keep a probability to perform non-preferred actions, but if you increase beta, with high beta, it will become very peaked so that you focus on the action you think is the best at a given moment. Okay, there were predictions from this, and I thought it could be interesting at some point to discuss this, but maybe I will keep them for the discussion. But just tell you, when we apply this to probabilistic tasks that have been learned by humans and so on, we predict that this produces an effect on the behavior that looks like, again, this inverted U shape that Roshan Kuls presented yesterday. So it's just to tell you that we could talk about this if you're interested later or so on. So now let's move to the third ingredient, and that's environmental characteristic. I told you the ITI and the duration of the ITI could play a role in this learning process. And the idea is that the animals in this Pavlovian conditioning task, during the ITI, they just have to wait. And it turns out that many times they go and visit the magazine, maybe just in case there's some reward. But each time they do that, because it's the ITI, there is no reward. And so what we hypothesize is that there's a disappointment at each of these moments. It's a negative reward prediction error, so that push them to revise the value of their expectation. So the probability overall to expect reward is decreased. And so if you have a short ITI, we proposed or predicted that this would enable only a few of those visits, disappointing visits, so less down revision of values. But if you have a long ITI, this allows the animal to have more disappointment, more disappointing visits, so more down regulation of values. So now, here is the model. It was quite long, but it gives you an overview.
A quick question. Do you also link that to something like an urgency signal? Or should I not mention that now?
Not directly, not directly. For me, it's more like the second mechanism. So I simplified to say that could be an exploitation, tuning, but actually, maybe there are different things here, and maybe there's an urgency signal. So there's more urgency, you want to focus more.
Right.
So I think, yeah, this could be related, but we are not making clear hypotheses. So it would be interesting to talk about that. So here is the model that we will simulate to account for the rat behavior. So again, you see it's a multi-system model. You have a model-based component that learns the internal model of the task, and a model-free system that will just learn values associated to these different cues. And each of them proposes different actions or responses, which will be integrated. And here there will be a weighting. So you have one parameter omega, which is the relative weight of the two. So if it's equal to 1, that means 0 contribution of MB, a lot of contribution from MF. If it's equal to 0, that means high contribution from model-based and not from model-free. And then, based on the output of this integration, we have a softmax action selection process. And here we're making the hypothesis that dopamine is affecting learning in the model-free system, but not in the model-based one, and expression through this regulation of exploration-exploitation trade-off. And so we model the task as a multi-state process, so what we call Markovian decision process. So the animals are waiting in an initial state, and when the lever is presented, they have the possibility to either go to the lever, engage with the lever, and when it's retracted, they go to the magazine to eat the food, and then there's the ITI. Or they could go to the magazine, engage with the magazine, and once the lever is retracted, they directly get the food and they can eat. So from an engineering point of view, the most optimal behavior is to go directly to the magazine because there are less steps. And that's why the model-based system that we will simulate will favor this behavior here. Or they could do anything else, like explore, wait, not move. And when the lever is retracted, if they have learned the task, they will go to the magazine, eat the food, and wait during the ITI. And so in that model, what the one strong message is like just playing with this weighting parameter, we can produce the behavior of these different groups of animals. So sign trackers, we explain with this model a half-half contribution, while goal trackers have a very low contribution of model-free, are very much model-based, and intermediate groups is something a bit in between. And I told you the model-based system will attract towards the shortest path, but here, because there's a Pavlovian component in the model-free system, the model-free system will very much increase the value of the lever, because that's a sign that predicts reward. And that will push animals that are very much model-free to be attracted by the lever. And that's why we think that will produce a sign tracking behavior. But if you have time during the ITI to revise down the value of the magazine, that will decrease the value of the magazine in the model-free system and make this contrast even stronger. So that's why we think the duration of the ITI will impact and produce even more strong sign tracking behavior. So with this model, I will overview. I think this is important. I have an important message. So like, okay, we simulated the thing. There are several parameters in the model. We have done some fancy optimization. Actually, it was evolutionary algorithm optimization. And you see we can get at the bottom curves in the simulated data that looks very much like the curves in the experimental data. But warning, I mean, when you have to sell your work, of course, you show the best curves and so on. But here we played with many free parameters. And somehow I want also to convey the message, like when you're doing computational modeling, you also have, as soon as you have several parameters, you can reproduce nearly anything. So we always have to be cautious. So first thing, we added an additional version of the work where we froze all the parameters. They were common to all types of agents. And we had only one free parameter, the omega. And you see in that case, of course, it's less nice, but globally we get the tendencies. So it's also important to do that type of controls to verify the properties of your model. And we can produce this change in dopamine fast-scan cyclic photometry activity. So again, so here in sign trackers, we have a nice propagation from the reward time to the stimulus that predicts it, and not in goal trackers. And in the model, when you can analyze afterwards, you see that it's because of this down-regulation of the value of the magazine that it prevents this learning, this propagation. And we also replicate this effect or reproduce this effect of flupentixol injection. So when you have flupentixol, you prevent learning in sign trackers in the model-free learning system. And when you stop injecting flupentixol, the behavior is still impaired. So it's really the learning process that has been impacted by flupentixol. But in goal trackers, when you inject flupentixol, in our model you have affected beta in the softmax decision, so you block the expression, but you see when you stop injecting flupentixol, the behavior is not different. So there was still a model-based learning process, which in our model was dopamine independent. And we've compared this model to different alternatives. We applied this to many different things. So that's one way of doing model comparison to really show that one model is better than others. Of course, there will always be yet another model you could think of that could best explain for the data, but of course, you have a limited model space. There are some limitations of the model, but there are also predictions. Now, it's interesting not only to have a model that explains previously published data, but you need to also raise new predictions and test them, because that's the challenging part, where you can invalidate your model immediately if they are not validated, if they are not verified, or you could maintain its plausibility. And the things that we were most interested in testing this impact of the ITI duration. So we predicted that reducing the ITI, so less time to down revise the value, should increase the tendency to goal track in the overall population. So the message would be like, it's not only that there are different individuals with different properties, but overall, some properties of the environment may affect the behavioral tendency in the whole population. And the effect that would mediate it would be to change dopaminergic patterns, because less down revising this value would reduce the impairment of the reinforcement learning process and would enable the dopaminergic pattern to reappear. Okay, so we had a project where we did this. Yeah, I still have time, and I have just a few more slides to show you. So we performed with our colleagues Matt Rush and Geoffrey Schenbaum, Donna Kalu in the US. They FSCV recordings of dopamine signals in the ventral striatum, so this histology. And the important thing is that they played with the ITI duration. So in the original study, it was 90 seconds. So here we're using a short ITI, 60 seconds, or a long ITI, 120 seconds. And all the rest of the protocol is identical to the previous publication. And so, interestingly, I'm showing, for the moment, the best results, because there are some behavioral results that go beyond the model and that the model cannot explain. But at least this change in the proportion of sign trackers and goal trackers, we see it. So there's a PCA index, which globally will be one index per individual, which is based on the average of response bias, whether they prefer the magazine or the lever, the probability difference between the two, and latency difference. So this is integrated. And so if the PCA index is close to 1, that means very sign tracking behavior. And if it's close to 0, or -1, I mean, it's very goal tracking behavior. And you see that with a long ITI, we have this distribution shifted towards more sign tracking. Although it's a bimodal distribution, so it's more complex than what we predicted by the model. And when you reduce the ITI duration, you see the whole population shifted a bit more to goal tracking. And that's significant. So that means, yes, the ITI has a global effect on the population to shift those tendencies. And very nicely, and we were positively happy about this and still surprised that it would work that well, dopaminergic reward prediction error pattern was affected by the duration of the ITI. So you can start by looking at the top right. And so there are early sessions from 1 to 3 and then late sessions. And so that's for the short ITI. And you see that shortening the ITI favors the appearance, the prediction of the reward, so that there's a decrease of the response of dopamine to the expected reward. It's well expected. So that's consistent with the theory. But if you have a long ITI duration, you see that this response to the expected reward persists. So that means playing with the duration of the ITI, we can affect this reward prediction error pattern. And now, interestingly, if you now divide into the different animals that have been categorized as sign trackers or goal trackers, you see that with a short ITI, we now have this response at the time of the reward for goal trackers, which starts to be lower than at the time of the stimulus, while in the original study there was really the same response. And reversely, you see that at the time of the reward, even for sign trackers, now there's a persisting response to the expected reward. So that means we are impairing the reward prediction error profile just by playing on the duration of the ITI, which is something super novel. So that's something that goes in the direction of the model. Of course, when you have a model, there are many limitations. So fixed parameters, many a priori information we put inside it. We can discuss about this. But I want to stress that it's nevertheless quite general model. So I've talked to you again about this general framework that we also apply to navigation, so to some operant learning tasks. Now it's working here in rats in this Pavlovian conditioning task, but we also applied the same model with the same parameters to a negative auto-maintenance procedure in pigeons that peck a light. So you have a light that appears and then they get some food. And because of this association, because of Pavlovian conditioning, the pigeons cannot prevent themselves from pecking the light. And even if you put this negatively, so if they peck the light, there will not be any reward. Because it's a Pavlovian system, it's really difficult to inhibit it. Similar to chicken that have difficulties having to go away from reward to get it. Usually the Pavlovian conditioning system is thought to be quite pre-wired, so that if you have something positive, a sign that predicts reward, it favors approach, engagement with this thing. And so, and interestingly, in previous papers with these pigeons, they saw differences between individuals, different behaviors, and that we could explain with different weighting of omega parameter. So it's interesting that the same model generalizes to other animals in that case. So that would predict that maybe there is also a coexistence of model-based, model-free learning in pigeons. So here I'm cautious because that's probably not the case. I don't know. Well, if you have more ideas on this, I will be happy to discuss. And the last experiment we did to further test the model was this an experiment to test the effect of dopamine blockade on the expression of behavior, so on this exploration-exploitation trade-off. So that's an experiment that we did with Alain Marchand, Étienne Coutureau in Bordeaux, and that was the PhD thesis of François Sinotti. So it's now an operant conditioning task with 3 possible actions. So it's a 3-arm bandit in the vocabulary used in decision-making these days. So there are probabilities of reward that are associated to each lever. So there is a low-risk condition with 1 lever associated to high probability of reward and the 2 others are very low. So it's easy for the animal to figure out what is the best lever. And there's a higher risk condition where you see the probabilities of the worst levers is nevertheless not negligible and makes the task even a bit more difficult to learn. And there are blocks of trials so that succeed to each other, and the animal has constantly to relearn, so each time it reaches some good performance, we shift to another block. Actually, it's fixed duration here, and constantly there's a change in the best lever, and they have to relearn all the time. And flupentixol was injected there with different doses to have a more or less strong blockade of dopamine receptors. And what we find in terms of performance in the animals, so probability of correct choice, you see that the more flupentixol you inject, the more you degrade the performance. And that's the case mostly in low-risk conditions, because in high-risk conditions, the task is already difficult to learn, and so it's difficult to see a difference. But in the model, when you perform model simulations, of course, it's very clear effect that you predict in both cases. Now, what is interesting is we fitted the model with different free parameters, a learning rate, this, again, inverse temperature that controls the exploration-exploitation trade-off, and another parameter which represents forgetting in the model. We fitted the models to each individual rat, and we looked between conditions of different injections of dose of flupentixol, which parameters were significantly modified to explain the behavior. And we see that it's mostly the exploration rate that is affected and not the other parameters. And to control that it's really meaningful what we observe here, we generated artificial rat behavior with different models where we imposed either the alpha parameter to change in time or beta and so on. And we wanted to verify that this method can recover the actual parameter that was changing. And when we do this, so here it's alpha that is changing, and you see that the method detects a significant change in alpha, but not in beta and alpha 2. And when it's beta that is changing, the method detects a change in beta, but not in the others. So at least that shows that when that verifies the method. So I realized maybe it has been a bit dense. I hope to have given you an overview of this modeling approach really at the systems level, where we need to account for quite complex behaviors, and we try to account for behaviors in different paradigms, navigation, Pavlovian conditioning, and so on. And in that case, to account for this variety of behaviors that we can observe and variety of dopaminergic activity that is recorded in the brain, we need to have different systems interacting in our models. And so the main messages from this presentation is that, well, when we do this, we not only can account for the behavior of a whole population, but we do see individual differences and different properties. So in the Pavlovian conditioning paradigm, there are those behaviors that are labeled as sign tracking versus goal tracking. We have worked on the hypothesis that phasic dopamine may contribute to model-free reinforcement learning mechanisms, which would be responsible for the sign tracking behavior, while model-based reinforcement learning may be independent from phasic dopamine, and that's how we explain things in the model. So now I know the story is more complicated, and some people think that dopamine also plays a role in model-based learning. So I'm happy to discuss about this and see whether we need to improve the model or not. And we also made the hypothesis, but also had some further experimental evidence that dopamine could also contribute to regulate behavioral expression through the exploration-exploitation trade-off, and not only play a role in learning. And that's a key ingredient also here to account for the data. And finally, and I find it very interesting because it's important to focus on the inter-individual differences, but it's also important not to only look at the individuals and look at what properties of the environment may also play. And so here, the duration of the ITI seemed to be a key ingredient to produce those patterns of behavior, sign tracking, goal tracking, and pattern of dopamine activity. So hence, the increased tendency to sign track within the population and the dopamine signals that were inconsistent with reward prediction error signal could be both explained by this different weighting of different learning systems in different individuals, but also the duration of the ITI. So I would like to acknowledge all the contributors of this work, the funding, and thank you very much for your attention.